and my postdoc, and Rafi Sevlian, my student. So the focus of the lab, if I had to put it in one sentence, is essentially creating sensing and control platforms to improve the performance of large-scale distributed infrastructure systems. And one of the main systems we work on right now is the grid, and from the perspective of electrical engineering as well as buildings, as well, and we also do some monitoring of transportation, which is also another energy question. Here are some areas, and I'll put this slide online. This is something I wanted to talk to you about how do I view addressing these types of problems. I have this very large system. I need to do something to improve its performance or integrate new types of technologies. So essentially, the way I see this problem is that we go through 4 steps. Initially, you want to make sure that you can monitor the system itself to get the state variables that you need to be able to say something about the system's performance. Then you want to do some type of model that predicts the behavior of this large system, and we will see what that looks like for the grid. And based on that model now, you can tell a lot about performance, and you can also start to think about how can I use feedback. And that can be standard, traditional feedback in the case of the power network, for example, adjusting all the generators, turning homes on and off. Or it could be less standard feedback, like sending messages to users over the cell phone to say, well, maybe your appliance is on without need now. Okay. Now, once you have these three things in place, you start to look into planning. For example, how do I expand my system? How do I incorporate new things into it? And I think what's different when you talk about infrastructure systems is that these things operate under a bunch of policy constraints. There are constraints from the city, the state, the PUC in the case of electricity, markets, and so on. So you have to take that into account in any model that you do. Okay, so I thought about what should I present, and I decided I will have kind of a mix. One is just a little bit of a high level of what I think is the smart grid, and then some different problems that we have worked on this area. Okay. So the grid today is something like a very traditional hierarchical system. It's kind of divided into 5 pieces. You have generation. That's all your standard coal and gas plants, and today we are adding some wind and solar and so on. That generated power gets transmitted using transmission all the way to nearby our cities. There we have distribution substations that bring down that power, the voltages and so on, to be distributed to homes and businesses. And inside your home, you have your end use. Okay? This whole chain here is controlled centrally today because it's assumed that you yourself don't have any other choice other than saying, I want to use power now. It also assumes that every generator can be told what to do, and it will exactly do what it's told. So there is a market here that coordinates how the generation and the end use connects with each other. That's this picture here. So, well, the reason for the market not being real time, which is every generator comes in and says, I'll offer power for this much money, and everyone who wants to use it says, well, I want to buy it for that much. The reason is because the grid itself has one constraint that you have to satisfy 100% of the time. At every single second in your grid, supply has to be equal to demand. The moment that does not happen, you shut down the whole power network for the US. So how to make sure that supply equals to demand? Well, then the way you're going to sell your power and consume your power has to go in stages. So first you run a day-ahead market where everybody comes in and says, what I want, what you may offer. So we all come and propose that. We say, okay, from your offers, I will take these particular generators, and users, I'm going to charge you this much for that generation. Then on the next day, maybe an hour before the time of delivery. So this market is run for every hour of the day. So from 8 to 9, 9 to 10, 10 to 11. So let's say we are selling now for 8 in the morning to 9 in the morning tomorrow. Another market is run again where people can now update and say, I really figured out that 8 to 9 tomorrow, I really want something else than what I said yesterday, so I'll adjust a little bit. The generators may say, well, my generator broke, I can't really supply that, I don't want to participate. So that's kind of this market. Then when the actual 8 o'clock to 9 o'clock happens, you enter into this stage where all the automated systems of the grid take over and ensure that we are always supplying what we consumers are demanding. Because we cannot predict perfectly the demand, but we have a pretty good prediction at this point, and we only get to know it when it happens. So that's kind of the short story. Well, now all of these decisions are made on this market. But once the power is all contracted, it has to go through this big network. So here are the generators. You have transmission lines. Then all of that power gets converted into various lower and lower voltages or various forms, if you want, until it gets to your home. And this network constrains how much each one of the generators can supply. It constrains how much can be consumed here, because maybe if these lines are all saturated and I can't send power anymore, I can't consume anymore here. Okay. And it also constrains the market here, because at this moment here, there's a big institution called the independent system operator that will ensure that all of these contracts go through this network. So they run a big optimization and tell everybody what to do. Okay, so that's kind of the story behind the market and how it interacts with these systems here. Okay. Now, there are two questions that I always have in mind when I look at a system like this. The first is to ask, what's the performance of this system right now? Let's say, right now, is there a way to know, are we doing good or bad with our grid? And the second thing is, what can we build to improve it? Okay. Here, I think some of these things were said before are just kind of the challenges when you start to put a lot of renewable generation. It has to do with markets, storage, limitations in the transmission and distribution, and so on. But given these challenges that we have in this new grid with a lot of variability introduced by renewable generation, what can we do? Well, the opportunity is that we now have a lot more information and control. We have new sensors. So we have smart meters at homes. Buildings have a lot of sensors. So for example, Y2E2 has 3,000 sensors measuring everything that goes inside the building. We have a lot more refined opportunities for control. So you can have appliances that are responsive. You can do demand response at the building scale, at the individual office scale, and so on. And tying sensors and control together, we have a lot tighter feedback. So we have a whole communication platform through the internet, as well as our cellular networks and other networks. So putting all of these pieces together allows you to go from something like this to something more like a network, where you don't need this hierarchy dictating what every single piece has to do. They can actually now coordinate over the network to decide on the best policy to minimize cost. But why would you want this instead of that? Because now if I have a lot of uncertainty here, I gain a lot by being able to coordinate consumption with production. Okay, that's one of the main reasons you want something like that. Okay. So the first thing that I want to talk about is sensing the grid. So that's answering the question, what do you need to measure in the grid? Well, the grid has generators, so you need to measure them. Measuring them means measuring the voltages and currents that are coming out of the generator, monitoring all these generators in detail as well for performance. You need to measure how much power is flowing in each one of these lines. Okay. You also need to make measurements about voltages at all these different pieces of your network, okay, all the way down to the consumer. So essentially, if you wanted to summarize in a very high level what the grid is in terms of a state, it is the state of all its generators, of all of its consumers, and all the voltages and currents across the grid. So these are all the things you need to know. Well, but there are additional things, right? Because we have renewable generation. So you need to measure now your weather. You need to be able to measure how much of the sun gets converted into solar power, how much of it gets converted to wind power. Building systems turn out to be more complicated than the voltages that you can input at them, because now you have the opportunity to control the air conditioner of a building. So now you need to measure your building. Similarly, in your home, there are appliances that will allow you to delay your consumption. So now you need to measure that. Well, now if I want to do something here, I need to measure you as well. And if you want to use storage to coordinate these things, you need to measure the storage performance. So you need a lot more measurement in the grid now, because we are trying to put these guys in and send power through this network. So what are the sensing challenges in general for all of this sensing? The first challenge is that since at every second, every millisecond, we need to make sure supply is equal to demand, we need to measure everything at a high resolution. That's the very first challenge, and that's an electrical engineering requirement. It's not a requirement of the markets, it's not a requirement of the utilities, but everyone who operates the grid knows that for making sure at every millisecond demand equals supply and being able to control the demand or the supply, I need to measure what's happening, and that means high resolution. The second kind of need now is that since we need to align demand and supply for every second, pulling all my sensor systems should only take me a few seconds. If it takes me 1 minute, a day, all of that devalues your measurements. So when you start thinking about sensor systems for the grid, that's one. The next thing is that you're going to operate on a noisy environment, and also you're going to operate in an environment there is tons of different equipment, different standards, and so on. So this is a big issue, having interoperability and the ability to do something in a noisy environment. And your data communication network now spans the whole country, or at least the whole state. And that's a big challenge, right? It's not everywhere. You're not going to get the same type of connectivity, and you need that connectivity to be available every hour or every millisecond, right? So you cannot allow, well, I can't send a packet now, great, so I don't measure my generator. Then I can't make sure that supply equals demand. So all of that is all great, but then power is so cheap today that installation cost becomes an issue. So you want all of these things. And I'll just give you some quick examples. So in our lab, we have been developing some sensors to measure the distribution system. The distribution system are the lines that come down in your neighborhood, supplying power all the way down to your home. And today we have 0 sensors in the distribution system. And yet we are putting all of these solar panels in there, which means there is power being injected in the distribution system. And without measuring that, you're not going to be able to integrate all of that power efficiently. It's going to cost you more to have solar than less, which is what you expect. So one way around it is to say, well, let's go and measure. If you try to measure one single pole near your home, this is all the equipment you need. It's about 500 pounds of equipment that needs to be installed there, okay? So we have said, okay, we will put all of that into one single small sensor that also does the communication and so on. And by the way, we use some better measurement techniques so we can get you a lot less noisier measurements of that. Now, what does this allow you to do? All of a sudden now, I know the state of my distribution system. I can coordinate all the homes, industries, and I can align their demand response. I can look for faults. I can do a bunch of things which you say, well, I expected those things to exist, but they don't. The next sensor we're developing, this is work being done by Rafi Savlian, my student who's here today, is a big challenge with renewables is that they are unpredictable. Now, to be able to predict better, you can do 2 things. One, you say, well, let me take whatever is measured today and develop a super duper statistical algorithm to do forecasting. That's what a lot of companies do, and there is a lot of research groups doing that. But what you find out in practice is that the limitation is the lack of measurements. Every wind farm typically has a single sensor. The reason for that is because you need to install this sensor at a 100-meter pole, and that installation cost is around $50,000. So that's the next. So what we are doing is, let's reimagine how we sense the grid, and we are developing a small sensor which you can attach to kites and balloons and so on and deploy to measure wind speed. So now let's quickly go into controls. I have about 5 minutes here. So the big question, the first big question in controlling the grid is that if I have measurements from my generators and I have measurements about the load, how do I dispatch the generation? Now, one thing is that we know wind and solar cannot be controlled, so you have to take them all as given. Well, right now, the way it's done is that you assume the wind that's going to get produced and the solar energy that's going to get produced is whatever you forecast plus 3 times the standard deviation of your forecast, or minus 3 times the standard deviation of your forecast to be conservative. You take that assumption and you do everything as if nothing is unpredictable about wind and solar. Okay. Well, what we propose is saying, okay, instead of that, why not just formulate the actual control problem, which is at every time here in my market, I get new information about how much wind and load I'm going to have. I can use those specific forecasts to optimize how much of the standard generators I need. And some work like that had been done in the past, but the controls were too complicated. So we said, let's simplify all the constraints that we don't care about and formulate the problem. And then we do some math. And what we find is that the rule that you need to use to optimize your grid is something like that. At every market, I'm going to schedule whatever I forecasted my deficit to be, that is load minus wind, plus some deviation amount. Okay? This deviation can all be pre-computed. They only depend on the statistics of your forecasting. Okay? Now, these deviations are specific to each location, to each forecasting system, and the performance of that system. And compare that to something like this, and you can see there is a difference. Well, what we found out when we did studies for EPRI is that you can essentially, if I had an oracle that told me exactly how much wind I need, okay, how much wind I'm going to generate, that's the best performance I'm going to have. And that costs me a certain dollars to get my deficit to 0. Well, on top of that oracle, my additional cost is only about $2.6 per megawatt. That compares to the cost today for integrating wind, which is estimated between $6 and $8 per megawatt. So just some simple control calculations can really help you here. So we are now implementing this as a software that can be used by the utility. Just to conclude, I wanted to show you something else. We all consume power, and we imagine that today we are all paying the same price. But some of us are nice, some are not. Right? So when you're thinking about that, you want to know, well, how much does each individual actually cost for the grid? And why do I want to know that? Well, because I have programs in my utility that I can target to different individuals. The way to do that is you formulate a simple cost model. The cost is, I'm going to predict how much you consume and allocate that much at a certain cost. And whatever I cannot predict, I'm going to have to pay a higher cost. Well, that turns out that then your cost to the grid is going to be given by some expression, which has to do with the distribution of your power consumption instead of a single number. Now, what we did is we took a lot of smart meter data, and we tried to see, are there standard types of people? And essentially, here's what we got. We get a lot of different distributions, and you can notice there's certain people here that you would like to target to improve your system. So just to say here kind of what is next, we are looking more into control problems, both for buildings and other grid devices.